Welcome. So the main idea of the session is to kind of get to know each other, basically. So we have conferences to speak to each other, but I think the conferences are way too large, and we've been through NeurIPS, and we all know the statistics. There are 30,000 submissions this time, and there's no way we get to know each other in that large crowd, right? So the idea here is to kind of narrow it down to smaller communities where it's more manageable, and we have more recurrent meetings where we can discuss more freely about the latest work. I think the key advantage is that we are talking about the latest work, not the work from 6 months ago when the paper was submitted. So another way I like to think about this is like a reading group, more international reading group, but with the authors present. So if you have any questions, you can ask the authors right away. We have to read the papers anyways, right? So please just come to the session and read it together. And if there's any question, ask the authors. So we are continuing this effort since 2 months ago. And we are continuing this on a bi-weekly basis. So there's an invitation. It's basically 2 week cycle. And so if you like, please come join after 2 weeks and so on, so we can kind of see each other on a regular basis. Okay, so with this, I think we are ready to get started. So Rayat, if you'd like to share whatever you want to share, if you have any presentation materials, please go ahead as well. Or
just give me a moment.
ECCV 2018. Where was that? That was before COVID time.
Yeah.
I think that was Munich. No?
Yeah, it was in Munich. Yeah.
Yeah. Okay.
Yeah, that's a old poster.
Yeah.
That's a very old poster. Oh, I don't know. I think what I should do is maybe this is better. Can you see my presentation?
Yeah. It's perfect.
Okay. So, hi everyone. I am Rayat Imtiaz Hossain. I'm a final year PhD student at University of British Columbia in Vancouver. So this is part of my PhD work. The work is titled Power of One. A single example is all it takes for segmentation in VLMs. And this is something I did in collaboration with my supervisors and also another collaborator. She was at UOIT, like I think it's Ontario Tech University in Oshawa. So basically, there have been some existing literature which has shown that the cross-attention maps or like image-text correlation maps, I mean, in general, these VLMs are like very good at this visual understanding or multimodal understanding, and they have very strong capabilities because of the way they are trained with image text pairs and so on. Especially the recent ones, the latest models, they're really good at visual reasoning. And there are existing literature which shown that you can essentially mine segmentation maps from these vision language models using either correlation between the image and the text features, image patch features and the text features, or like from cross-attention maps. Basically, these can be, we can categorize them into 2 different categories. One is like clip-based. Well, clip is also a vision language model, but like I've just differentiated into 2 different parts, like clip, like which is totally clip dependent. And then there is another version, which is like VLM based, which generally exploits general VLMs like Blip or like Lava. And you can further categorize them into training free categories and like ones which are designed particularly for segmentation, like OMG, Lava, and SEAM. And these models, like which has explicit segmentation decoders that has been trained with segmentation annotation, whereas these the first category, they are not actually trained for segmentation tasks in particular. So the limitation of the existing approach, as you can see, like most of them are either entirely model dependent, like for example, clip dependent. So you cannot like generalize to other type of VLMs. And even these clip-based ones, they require like really extensive prompt engineering. Also, the ones that are VLM based, like which are training free, one of the key issues here is like, if you look at the cross attention maps or the attention maps of the VLM, you'll see that not all layers have equally good grounding between text and image. So these approaches usually go through some manual selection of layers, either by like, using a validation set which has labels, or like, using another external segmentation model to generate pseudo ground truth and try to come up with a layer that has the highest MIOU with the pseudo ground truth and like basically extract the map from those layers. Another issue is that a vast majority of the work, which kind of uses LLMs or VLMs, they kind of train a very complex, not necessarily complex, but I mean, special decoders for segmentation, and which are especially trained for with segmentation annotations. So basically, they instruction tune these VLMs for those particular tasks with special decoders and annotations as well. And as you know, in certain domains, getting dense annotations, pixel level dense annotations can be challenging, especially in the medical field. Another key downside of these existing approaches is that they tend to use external knowledge to reduce false positives, especially the training free ones. So for example, they might ask external model like ChatGPT or like very powerful LLM to just show, just ask a prompt like what classes are present in this image. And based on the answer, they only, use that. So basically that's a way to filter out the false positives for them. So in this work, our main contribution is we are extracting segmentation from image text attention maps of vision language models in training free manner and can be applied for open vocabulary segmentation. We proposed an unsupervised training free entropy based metric info score to select the optimal layers for segmentation. Basically, this info score is actually based on two different entropies. One is the image level entropy, another is like dataset level entropy. So the goal here is to kind of select a layer that has a low image level entropy so that, whatever predictions it makes are confident. And at the dataset level, assuming that they are like evenly distributed, like although it's not necessarily the case for segmentation, but we have an assumption that throughout the data set, all the classes are equally likely. So at the data set level, we want the prediction to be fairly uniform. So we want to maximize this ratio of like, data set level entropy and the image level entropy. And whichever layer maximizes this ratio is selected as the optimal layer. So basically, once we select these optimal layers, we have shown like, yeah, we can do training free. But even if we provide a single example, visual example for each of these categories, you can see a substantial improvement in performance. And that's because like sometimes the class names can be pretty ambiguous and very difficult to like semantically discern from text, especially for finer grained categories as well. Another advantage that our method has is like we don't need any external knowledge to do the false positive filtering. We're using model's own knowledge to do that. So basically, this is an overview of our approach. Basically, given these text prompts like image of bicycle, image of person, and so on, we use the info score to select the best layers. In the training free setting, we only extract maps from those layers and basically take an ensemble between them. Basically filter out with class presence probability, which is basically you can use the model for the models which are trained with image text matching loss. You can use the image text matching scores. And for models which are not trained with that, you can basically ask questions like, is bicycle present in the image, yes or no? So based on the probability of the yes, of the prediction being yes, you can like use that as a proxy for the class being present. Now, for the one-shot tuning case, you can provide single example for each of these categories. And all we need to do is fine tune these text embeddings and the layers that we select and nothing else. So we don't use any additional decoder or any additional parameters. We are just using the parameters of optimizing the parameters of the VLM as is, and we get a substantially improved performance. So I've already kind of gone over the info score, the actual goal of the info score. Here it's more in more detail. So that image level, as I said, like we want the classifier to predict confidently. So you want outputs to be peaked across certain classes, not over all the classes, and at dataset level, assuming that it's independently distributed, like we're assuming like that all the classes are equally likely at dataset level. So yeah, we are aiming for a more uniform distribution or higher entropy. So whichever layer maximizes this ratio is kind of we consider them as the optimal layers. And here we have an ablation of layer-wise performance versus how our metric selects the layers. So as you can see, in many cases, our metric was perfectly able to select the best layers, best performing layers in general. So even though it's unsupervised, it's kind of performing a reasonably good job in extracting the best layers. And another good part about this is like it's also generalizable to different data sets. Like you don't really need a sample data set or a gold data set to do that. So if you have some data set, you can basically compute the info score for them and select the best layers for them. So as you can see, if we combine all our components together, we get state-of-the-art performance on 3 complex datasets like COCO Object, COCO 171, and ADE. And if we just provide a single example, you can see that there is a substantial improvement in performance. Because as I said, some of the words or some of the class names can be pretty ambiguous. For example, one example that I can give is there is a class in COCO called tie. Now, it can be a verb and it can be noun, or tie can be a very ambiguous class, but what it actually represents is a necktie. So, so yeah, certain classes can be very, very ambiguous. Here we kind of show the effectiveness of our InfoScore selection. As you can see, we compared our InfoScore-based selection against naive selection, naively selecting the last two layers, or randomly picking one layer, or combination of all the layers. And as you can see, our InfoScore-based selection is more consistent in giving us the better segmentation results. Here we also showed performance across different VLMs, even the latest ones like Lava. And as you can see, there is always a significant jump whenever we provide a single image example. Here we also show the effectiveness of image text filtering, where we are using model's own knowledge to filter out irrelevant classes. As you can see, without that, the performance significantly drops. But when we do that, there is a significant improvement in performance, particularly in the training fee setting. But in case of one-shot supervision, the impact of that becomes less because we have visual examples to make up for it. So yeah, that's it for my presentation today.
Thanks a lot for sharing the interesting work. So typically, if there's any kind of quick factual questions, we do it now. Otherwise, we keep more longer discussion for the later part of the session. So thank you. If there's no quick questions, then we can move on to David for now. And yeah,
okay.
Please share.
Thank you for the opportunity. Let me share my screen. Okay. Okay, you should be able to see my screen, right?
Yes.
Okay. Okay, so thank you all for the opportunity. Today I'm going to present our recent submission to CVPR, which is entitled Seeing the Abstract, Translating the Abstract Language for Vision Language Models. And this is a joint effort with my colleagues, Federico Girella, Daniel Liu, Marco Cristani, and Yiming Wang. So we started from a problem that we had in the fashion domain. And in particular, what we observed is that there might be different ways we are describing the same data. So in this case, we were having description from fashion expert, which were mainly relying on abstract terms, abstract adjectives. What do I mean by abstract adjective? By abstract adjective, I mean something like different, sexy, airy. So like properties, attributes, adjectives that are not that easy to ground in the image. And so it's something that you cannot really perceive or act upon. And this is the kind of the definition that they give in the psychology literature to these kind of words. And so these were kind of adjectives that usually depend on other words to be described, but they're useful in order to convey emotions or feelings. On the other side, we observe that alt text is mainly characterized by concrete-oriented adjectives. So they mainly rely on attributes and adjectives that are measurable and you can really perceive. So, for instance, an example might be sleeveless top, which is it has no sleeves, or the fact that the top is loose on the waist. So we observe this difference and we try to understand whether it has some impact on vision language models. So in particular, we try to understand, okay, first of all, let's try to understand whether abstract or abstract adjectives might be useful or not. And to do that, we constructed an experiment in order to understand in an ideal retrieval system whether abstract adjectives are able to convey information. And to that, we consider an ideal system where images are retrieved based on the attributes they have. So in practice, we try to understand how uniquely the description is characterizing a particular image. And what we observe is that if we have a large presence of abstract adjectives in our description, we can notice that the retrieval performance is improving. So in practice, we observe that abstract attributes, abstract adjectives are able to make the description more discriminative. And we do observe this trend with different description length. On the other side, we try to understand whether VLMs are able to handle and to cope with these abstract adjectives. And to do that, we try to understand the difference between trying to retrieve images based on on concrete or abstract adjectives. So to do that, what we started from multimodal data coming from Fashion Expert, which is abstract oriented, and we generate some description by using VLMs to generate the concrete counterpart of this description. In this case, we have two different description types which are described in the same data. And what we observed is that concrete-oriented description are much more powerful at retrieving and describing this data. And we observe this trend with different VLMs. And not only with general purpose VLMs like CClip or OpenClip and Clip, but even with the fashion specialized ones, which are available in the literature like a Fashion Clip or Open Fashion Clip. So what we observe is that visual language models nowadays are struggling to handle and to cope with these abstract attributes, these abstract adjectives. So this to give you an idea of our intuition. We didn't dive into the motivations why this is happening, but okay, on the top we can observe the kind of attributes that we consider to be abstract or concrete based on the results from the psychological literature. And on the bottom part, we can see a study and some statistics about the presence of attributes and their nature in different data sets. And like in the first two rows, you can observe that fashion datasets have a large presence of abstract adjectives, but on the other side, if we consider large-scale data like Lion, which is based on alt text, we can observe that they have a larger presence of concrete occurrences, and that the difference in the presence of concrete attributes is much larger. Okay, so they are concrete oriented, we say, because they have a large presence of concrete terms. So starting from here, we try to understand what we can do. So the idea was, so our intuition was, okay, so starting from the abstract description that we have, we might have that the model is not really able to cope with these adjectives. And so we end up with some representation of our description, which is far with respect to the image embedding. So starting from there, we decided, okay, what we can do, we can try to understand what is the difference between the abstract-oriented and the concrete-oriented description, and try to move and augment the embeddings coming from a VLM representation in order to make them closer to their image counterpart. So in practice, the general idea is that we construct paired data where we try to describe the same visual data in different ways. On one side, we have concrete descriptions. On the other side, we have abstract descriptions. And then we try to characterize what is the difference between the two types of description. And finally, at inference time, we can augment the original representation by using this shift. So I'm trying to give you an idea of the strategy. So on one side, we follow what we did in our pilot experiment. So we use a captioning model in order to generate the concrete counterpart of fashion data, of fashion images. And so we have paired data where we have concrete and abstract representations. And then we try to characterize the dominant differences between these two representations in the latent space. And to do that, we use dimensionality reduction technique, and we rely a lot on the normalization characteristics of the different manifolds in practice. And finally, what we do at inference time is that we try to make the representation more concrete, closer to the image representation. And to do that, in the initial phase, we use a large language model in order to rewrite our initial description in order to make it more concrete. But as this is not enough, we rely on the shift in order to augment our original embedding and to make it closer to the visual representation. So here, I think it's a nice representation of what is happening in the latent space. And here we are trying to visualize on the orange, with the orange color, we are trying to convey the abstract description is the latent representation of abstract description. On the blue, we have the latent representation of concrete descriptions, and with green we have our augmented representations. And as you can see, for paired data, we have that concrete description and abstract description are completely separated in the latent space, where they are much more blended in the augmented space. And as you can see, even in the natural language, we can show that the representations are consistent. Okay, and then finally some qualitatives about how we are able to cope with these abstract adjectives, which are conveying style, emotions, and so we are able to condition our retrieval based on these abstract adjectives. Okay, that's it from my side. Here you can scan a QR code where you can check code, data, notebooks, and everything is there. But if you have any questions, I'm glad to answer.
Thanks a lot. So if there's any question from the audience or from the other speaker, yeah, please go ahead.
I mean, it's an interesting work. Yeah, it's really interesting the fact that you're trying to like associate the adjectives with the like, because those are like very difficult to ground. And I was just wondering, like, have you tried with the generative models, like, or do you have any plans to extend it to generative models like diffusion models? Like whether you can generate with those kind of adjectives, like more adjective centric generation?
Yes, I mean, this is in the plan, but at the beginning we thought, okay, in order to properly condition the generative model, we need to have a good representation of our text. So in the initial phase, we thought, okay, we need to work on the representation of the text at the beginning, and then later we can use it for conditioning a diffusion model in practice. But that's a good point. Thank you.
Yeah, no. Yeah, totally makes sense. Yeah, I kind of got I think I kind of realize that that might be your motivation in the long term, because yeah, I mean, this is very interesting. Thanks.
Another question from my side. So do you know, so maybe you shared this already, but how do you evaluate the retrieval for these kind of
We
abstract?
mainly okay. I didn't show here the classic retrieval results. If you check out the paper, there are some retrieval results, but the idea is that we do classic retrieval and we evaluate using retrieval metrics. We want to correctly retrieve the item we are trying to describe it with the natural language. So it's a text to image retrieval in practice.
I see. I mean, there's typically this problem of sparse annotations for retrieval, right? So maybe there are some pairs of text and image, which also kind of makes sense, but somehow these are not kind of captured in the.
And we mainly rely on data coming from websites, which usually are much more verbose. And so, I mean,
I see.
we never checked, to be honest. I mean, one of the pilot experiments that we had was really relying on how the description is uniquely identifying your image in practice. But to be honest, I never checked rigorously how many images you can describe with the same description in practice.
Mhm, mhm, mhm. Yeah,
Yeah,
I was
that's
wondering
true,
because.
but that's I would say is a general problem where you have
Mhm,
text to image retrieval, right? So
mhm,
especially for valuation.
mhm. Yeah, if I may continue, although I try to ask less questions and give it to the to the audience. But another question from my side is so now it's more at the factual level. So you're computing this kind of global difference between the abstract and concrete text, right? So is that a single vector for the entire data set, or is it kind of
Yeah,
more
yeah. So
fine-grained?
far we are considering one single vector for the entire data set. A nice extension would be, let's try uh, to make the shift conditioned on the kind of abstract attributes that we have
Hmm, hmm.
at hand. So what would be, for instance, the correct shift to represent an happy T-shirt or an edgy jacket? So based on the kind of abstract, it would be nice to condition the shift based on the abstract adjective you're trying to map in practice.
Yeah, interesting. It'd be interesting to also like there is a natural conditioning here which is given by the data set itself, right? So I would be also quite curious to know like if the this kind of steering vector or kind of conditioning is also transferring to other kind of data sets.
I mean, we tried. Our main objective to go training free was trying to make it cross data set in practice.
Ah, okay.
Yes, but I mean, we have experiment with that and it's working nicely. Of
Okay.
course, not all the transfer are possible. I mean,
Mm.
it's, and I would say that the weakest part of the method is like the language rewriting. If you have the language rewriting made with language models, so language models um, might be tricky for language models to try to make it concrete in practice.
Hmm, hmm, hmm,
But that's interesting future work, that's for sure.
hmm. For sure, yeah. And I also have one question for Rayat, or if you have any question, please go
Yeah,
ahead.
I have one more question for Davide. I mean, along that line. So I was just wondering, did you have what language model did you use to generate this like more concrete properties from the abstract, given the abstract ones? Like, I guess you
Um,
provided some in context examples.
I mean, we did a lot. We did a few ablations on that, and if I remember correctly, I mean, the one we used for the method was Llama 3 in the end. Llama 3 with 8 billion parameters.
And did you do any kind of like reliability analysis of like how reliably these language models, like given the in context prompts, like how reliably they're generating these examples? Or is there any kind of
I
analysis like?
mean, yes. I mean, we had problem. I mean, we are trying to extend to other domains like air art, for instance.
Mhm.
And there, trying to condition the LLM is quite tricky. Yeah, so they might hallucinate a lot, especially if your in context samples are might not really faithful about the task that you are trying to do.
I see. Okay. Thanks.
Thank you a lot.
Yeah, so thanks. So one question from my side for Rayat was about the use of one sample for training this system. So I was wondering, so maybe I missed the part where you were using the one sample. So what kind of information do you extract from this one sample?
So basically, by one sample, I mean we provide one example for each class. Say if there are 5 classes, we kind of provide one example for each of the 5 classes, and we provide the ground truth annotation for that single example.
So
And there's no language part, right?
There's also
Image and ground.
no, the prompts remain the same. The prompts remain the same. The only difference here is like now you are providing an additional image. Whereas like previous case in the training free session, there was no training, right? Here,
Yeah.
like you with one single example.
Mhm.
Also, like to make sure that it's consistent with the few shot literature, I mean, they're very strict in like how you process the image. For example, like if there are multiple classes co-occurring, they usually label one of the like exemplar class only that has the mask, and the other ones are labeled as either unlabeled or like background. So we follow the same protocol here as well, just to make sure that we are not getting an unfair advantage. Although in practice, though, you can technically say have single image which has all the 5 classes present in the image. So you may not even need 5 different images for those cases.
That's an interesting idea. Yeah. Maybe you can
Yeah.
just have a collage of all the images in a single image.
Yeah, exactly. And this is more prominent in certain classes which are not designed, certain data sets which are not designed for few shot segmentation. For example, Coco 170, 180, 20K, they have like 171 classes and 150 classes respectively. That's a lot of classes, and a lot of these classes are staffs classes, which means like they always occur in some form. Like those are like always present in background. For example, wall, or like there are classes like wall, then floor, ceiling, and those kind of things. Like if you are looking at an indoor scene, these classes will always be present. So you cannot really remove them in any ways if you are working with indoor scene. So in such cases, we, to ensure fairness, what we did is like, say, for example, like we can never find an image where, like, say, there is a table, but there's no floor or something like that. Like it's very hard to find that, and it's kind of labor intensive.
Yeah.
So what we do is like, if we find an example with a table, like just use the ground truth for the table, and for the rest of the things, we consider them as unlabeled. For the floor, we just pick another example where like we just give an example of the floor and just give the annotation mask for the floor. For like there might be other images, but they are like labeled as unlabeled. The one thing is that it kind of limits the model's ability to learn, because it is not being able to exploit the co-occurrence relationship between different classes, which the segmentation approaches are like almost like these methods which are trained with segmentation annotations. They have this like exploit this co-occurrence relations. Whereas for our benchmark, it is something that we haven't done, and it's mainly to show that to maintain the consistency of the few shot paradigm. That's it. But yeah, technically you don't really need 5 separate images for 5 classes. As long as you have minimum number of images that contains all the classes, that should be fine. In fact, I think that would be even better, because like that way you kind of exploit the co-occurrence. For example, like if you have a table, there is a high chance of having a bottle on the table or a cup on the table. So these classes always tend to co-occur. So yeah.
Yeah, thanks for the insights here. Maybe following up on the your comment on the fairness, right, against the prior work. I think it's quite important, but at the same time, sometimes it's a limiting factor in practice, because I don't think kind of having a single image with the ground truth segmentation annotated is the most efficient way to kind of
I think a better way would have been, honestly, is like, try to get a small subset where you have like at least one examples from each classes. So some classes might have 2 or 3. But then again, like you want to make sure that you have enough samples that has at least one, like each of the classes are present at least once. So that way, I guess like it could have been formulated in that way. Yeah, as well. I think that might have been a better formulation in some aspects. Yeah.
So if you want to distill the knowledge in a smallest subset of samples, then your choice would be to kind of maximize the diversity of co-occurrence patterns.
Yeah.
Okay. I see. Yeah. That's always the problem, I guess, for vision recognition systems. Like the co-occurrences are kind of super difficult to resolve.
Yeah.
Especially low sample. Okay.
I have one question. I'm not sure it's like on the evaluation protocol for few-shot learning, but like, have you checked how the model performed when you on other data on other classes that you are not few-shotting?
Yeah, we did an ablation for like, for example, we train on 25% of, like we provide example for 25% data and like see how it generalizes to the rest of the unseen 75%. It generally, there is a general increase in performance in general, because like not only on that 25%, obviously you will get improvement in 25, but it also like kind of helps you learn better maybe text representations, and like there is an I mean, there is an ablation that we have done we provided in the supplementary. So you can, if you go to the the arXiv version of our paper, you can see in the supplementary there is an experiment where we kind of have divided into 4 different subsets, and like where we train with 25% of the classes and evaluate on the 75% of the classes.
Oh, that's nice. But what's the intuition behind the improvement? I didn't get it. Sorry.
I think the intuition here is like, once you are able to correctly classify those particular classes because you have examples for them, there is less confusion with those classes, between those classes, the seen classes and the unseen classes. So I mean, that kind of confusion, I think, in my opinion, gets reduced. That kind of helps to kind of slightly bump the performance on the unseen classes. It's not a massive raise, obviously. It's a slight bump, more like. The more importantly, the performance doesn't degrade, which is what's more important, I guess.
That's nice. That's nice. Thank you.
So another question that I have is, so I used to work in the domain of segmentation before the clip era, but now I stopped following this more or less. But before this clip era, we used to kind of separate the performance in terms of kind of whether you can localize the object at all, or whether you can delineate the contour of the object more cleanly.
Yeah.
So how do you assess the current state of the art? Is it?
I think most of them are like about delineating, mostly, like how close it is to the actual segmentation annotation, rather than like if you can localize, like not MAP. It's more like the MIOU, the intersection between the ground truth, which I believe like can be because like, you know, these, if you look at even like COCO annotations, they are very noisy. Like I personally looked at cases where like there was this image where there was a, you know, these like trucks have these like huge bumpers, and within one of the bumpers there was a tiny cat, and they didn't label the cat at all, and it's entirely labeled as a truck, so which is wrong. And my model was correctly predicting the cat, but yeah, obviously like now I have a lower MIOU, but like this is
it's gonna penalize a lot.
Yeah.
Actually. Yeah.
That kind of happens. So maybe in certain cases, like you may end up like the models which has learned which has overfit on this particular data set may perform better. I don't know, but yeah, there's always this issue with annotations.
But what about in your context where you have only low budget for annotation? Do you still suffer from this, or put in another way, is it still
that's a good
dominated?
point, honestly, because like for low budget cases, I mean, we don't suffer in general like that, but the thing is that there can be cases where, you know, certain classes kind of dominate, especially like, you know, certain classes might occupy larger amount of area, and other classes, like, you know, occupy a smaller portion of the area. For example, if you're talking about com or like scissors, those are like really small in general in the image. So the smaller objects often become harder to classify than the larger objects. Like by larger, I mean usually most of the time, like scissors appear very small in an image. So there is always this issue with like in any kind of few shot literature, like they kind of struggle with smaller objects. Like for medium and large size objects, they are fine, but for the smaller ones, they find it difficult.
So in your opinion, is that the problem with the model architecture or the data?
I think it's this data as well as model architecture as well. I think one of the things that I really wanted to explore, but it eventually didn't, but was like how we can somehow balance out the, in classification, in traditional classification, you want to make sure that like you have one like equal amount of examples for all the classes. But for the pixel wise classification, you cannot do that because like you have like essentially like certain classes which has like a lot of pixels. So we have like a lot of annotations for that. Whereas for scissors and books, A, like there are few examples, B, like they occupy a small proportion. So is there any way to kind of balance out these disproportion in some way? Like that would be an interesting avenue to explore, and certainly like that would help. But I guess like these days, like people have been like, trying to kind of look into these fundamental problem less and like trying to more into kind of different sort of things. So I kind of tried to pivot from that.
Like
but I guess
in,
like, yeah.
Zooming in. I think the images have high resolutions nowadays, so zooming in is not a problem.
Zooming in is not a bad example, yeah. But I mean, I guess like if you have these classes, maybe you can crop and zoom in, like have a cropped version of those classes so that like you can balance it out. And then like, yeah, there's always this like, if you look at any segmentation data set, like it's very long tail distribution. It's not even at all. That's a huge issue. And the thing is that because we don't have a prior on the data set, like, I mean, if we had a prior, then it would have been easy to like, assign weights in that way for the classifier. But yeah, if we can find out some sort of prior, maybe, yeah, that would be nice.
So yeah, as you said, I feel like the current limitations are not so different from like limitations from 4 or 5 years ago, actually.
No, it's not different. People haven't been really, it's more like nowadays the approach has been like, yeah, throw in more data and more annotations. Like if you look at the segment anything and all this kind of models, the approach is like, try to train with as much data as possible and then try to like get around those issues then. That has been the kind of approach these days.
But again, asking the same question, do you think the problem is in the architecture or in data for this?
Well, there is definitely problem in the data set itself, but we can definitely tune our architecture in such a way. Like the architecture itself is not problem. The learning approach is the problem probably. Like we can like, for example, as I said, like if we can have a prior of how the classes are distributed in some way, if we can like extract the prior in some way, then we could potentially like assign weights to the classifier in that way. Like, for example, we know like these examples are more scarce, so we assign more weight to that. Whatever examples we have for that. Whereas like, that this like there will be a person in almost every image, so assign probably less weight because like to that person, because like you will eventually see a lot of examples. So if we have that kind of prior knowledge, and that's something that, if we can come up with something, a nice prior would be nice, like if we can exploit those kind
maybe that can be kind of optimized as well using some black box optimization or something.
Exactly, yeah.
Interesting. Maybe that could be an interesting kind of follow work. Interesting. Any other questions? I think I was speaking too much. Yeah. Otherwise, I was also wondering about the approach for Davide. I'm jumping kind of back and forth. So I was wondering about so to be honest, I didn't fully get the adaptation part yet. So you have this single vector for the difference, and how is that used for adaptation to to the kind of abstract query again. So
in practice,
you have LLM for. I remember that you have LLM for kind of translating that into more
yes,
concrete
in an
language.
initial phase, I'm translating with an LLM. I'm doing the rewriting into a more concrete description, and then we applied in the embedding space. We apply this shift by simpling what we do in practice. That we try to get the main components by doing PCA of the difference of these two spaces. We project these. We project the representation on this space, and we apply this difference in practice. We normalize, and then we normalize.
By applying, you mean just subtracting this from the,
Yes,
or adding
practice,
this
yes.
to.
In practice, yes. Yes.
Okay. Okay. So does that tell you, I mean, I've seen similar approaches in different applications, right? When there's a difference in the, there's a rift between image and text embeddings, right? Then you just try to translate one of them to the other. And that seems to kind of match the space, sort of. Yeah, I'm just wondering if the steering vector, so in that case, the vector difference is from image domain to text domain. And I was a little bit confused here whether the difference here is taken between image and text again, or is it?
Oh, here we, since in initial phase we construct a database where we have paired data. So, and by paired data I mean that we have, okay, we have the visual information, so we have the image, and then we have two different descriptions. One description is the one from the data, which is abstract oriented, and another one is generated by using the bias of VLMs for concrete oriented descriptions. So we have two different descriptions. One is abstract oriented, one is concrete oriented, and we compute the difference between abstract oriented and concrete oriented descriptions.
Okay, so it's based on the text space, and so you don't do any kind of explicit matching between image embeddings and text
No,
embeddings in
no,
this
we
case.
just get closer into concrete oriented descriptions.
Interesting.
Yes.
Okay. I'm also curious, like whether you found any kind of geometric, kind of funny, interesting insights, whether the abstract embeddings are kind of more spread out than, let's say,
I mean, what we observe is that they are completely separated
okay.
from abstract ones are completely separated from concrete ones. This is what we observed, and yeah, and in general, what we observe is that image ones are easier to match to concrete ones. This is what we observed.
Yeah,
But of
yeah.
course, if you check the space all together, so the descriptions and the image descriptions, so the image embeddings and the textual embeddings, the representation would be dominated by the concrete the modality gap in practice. So we'll be challenged to see this separation with visual embeddings too.
I see. So you're saying the text to vision is much bigger than the
Yes,
text
yes,
among
yes.
different types of
Still
text?
they are closer.
Ah,
Text to image is much
that
larger than concrete versus abstract.
yeah. But also I'm yeah. Um, yeah, that's interesting. So I was wondering whether that, so you showed the statistics of Lion versus the fashion data sets. Um, maybe that's one reason why there's a bigger distance between the abstract kind of descriptions and the images. But do you think there's inherently something about the abstract descriptions, like maybe these are more abstract, as in the name, right? Meaning that maybe for the same description, there are many images matching to the same kind of like similar description. So somehow it's somehow hard for the model to tie those descriptions to specific image closely, and somehow it has to be kind of spread apart. to
I
accommodate
mean,
different
that
possibilities.
that might be something, that's for sure. That might be a problem. So trying to ground the information in the visual space, right? That's for
Yeah,
sure. But I think even I mean, since we observe the statistics on the textual descriptions, I mean, and I feel like going abstract requires a bit more commitment in the kind of descriptions that we have. So meaning that much more effort to write something into abstract terms, probably,
I
because
see.
it requires like conveying emotions, feelings, and this kind of stuff. But that's my simple intuition.
I
Uh,
see, but that's really
Complicated
valuable.
it is.
Hmm. Having seen a lot of examples by yourself, right?
Yeah.
Hmm. Interesting. So yeah, maybe it's also more subjective, right? So maybe different people come with different descriptions for abstract descriptions.
Yes, that's true. That's true. At the beginning, we had a lot of problems trying to make more concrete what abstract means, and
Hmm.
still
Hmm.
we were a bit undecided whether to go for. But then it's something is a concept which is already well defined in
In
the
psychology,
psychology. Yes,
I
where
see.
they do really have some kind of human data collections where they try to ask humans how do you feel this is something concrete, how so they define the concreteness of a word and they collect the rating of different people.
Hmm. So you mentioned two interesting criteria for abstractness. One is localizability or kind of non-localizability, I would say. And the second one is, I think, subjectivity. Was that right?
No, I mean, mainly the definition is like on whether you can act on it or not,
Oh, okay. Hmm.
or you can perceive it with the
I see.
faculties.
Hmm. Okay. Whether you can act on it. Mm.
Yes.
That's also quite abstract.
Yes, yes, yes.
Hmm. What if you can act on airiness of the no, maybe I'm not getting the definition clearly.
I mean, you, concrete terms are those that you can perceive mainly and you can measure and you
Yeah,
can get them with the senses. So it might
something that can be
be,
measured.
yeah,
Yeah.
it might be the touch, it might be the with vision, it might be with the taste, whatever. And
Yeah.
on the other side, we have abstract adjectives, which are mainly defined in terms of other concrete adjectives in practice. They
Hmm.
are constructed from other adjectives.
But eventually, the input given to the system is just visual. So the rest of it, the abstract descriptions, are kind of coming from the interpretation. So I'm just wondering, like imagining human in the loop, right? Where the human is looking at the system, sorry, looking at the image and trying to come up with a description. Maybe there it's not just about the input, but input image, but also about the yeah, surrounding situation for the human. Um, is that right? And so if that is the kind of the description, then um, are we kind of asking the model to kind of reason about potential hidden information that is not given to the model?
I mean, to some extent, yes. So in practice, what we are trying to do here is like we are trying to allow the model to map these abstract adjectives into the visual domain in practice.
Hmm. Hmm.
Um, because it's like a convention. So so we are assuming that the people is like using this word as a convention. So since people can align on this on the definition of a specific adjective, so we can use this convention in practice. But in what we are trying to do, we are trying to still map these abstract adjectives into their concrete counterpart.
Hmm. Yeah, interesting. Okay, maybe that has a lot of ramifications, implications in other domains. That's why I was interested in this as well. Yeah, also the geometry perspective of the embedding space is also something that I'm super interested in personally. Okay. Any other questions or? Yeah, otherwise I like to keep like 3 minutes at the end of the session to kind of close it. So first of all, I like to thank the speakers again for sharing your work. It was really enjoyable and interesting. And it's nice to see you, and I wish to see you around in the next conferences and so on, and in the next Connect sessions as well. I like to kind of share the feedback link to make sure we get all the feedback from the session to improve upon the previous sessions. We are at the early stage of this session, so your feedback is essentially shaping the future of these events. We will send out invites to people who publish their paper on arXiv, right? So if you publish a paper on arXiv, then you will basically expect invitations on a regular basis. Apart from that, the session is recorded, right? So the plan is to put this on YouTube after some editing. But of course, you can opt out if you want. Just let us know if you wish to opt out even at a later stage, and we'll handle this. Yes, so this is basically it for today, and thank you so much for joining.
Thank you all. Bye.
Thank you.